My name is Pawel Wojcik, and I'm the founder and managing director here at RedoxMe. And I'm going to talk about this the path to innovation in electrochemical tools. So I will just give you a short introduction to the company because it's the first time I'm speaking to this audience. And also I will tell you why we do things differently and how we can accelerate development of catalysts and how actually we are doing this. So the company was founded in 2015, and that's a spin-off from Laboratory of Organic Electronics at Linköping University and also Research Institutes of Sweden. And we basically design and fabricate highly specialized setups for electrochemistry. And in those setups, we combine electrochemistry with other techniques like optical, thermal, electrical, and many, many others. So we promote a good practice in measurements. Of course, we provide those products, and also we allow deep customizations. And we developed around 50 different products addressing many different fields of electrochemistry. So I will just briefly show you our portfolio. So we have those electrochemical cells, basic electrochemical cells, and also the ones that we can integrate with quartz crystal microbalance, and then photoelectrochemical cells, all possible types of spectral electrochemical cells, and also tools for batteries and supercaps, screen printed sensors, desalination, and also reactors for electrosynthesis, and many, many others. But together with those equipment, we also provide laboratory instrumentations because there have to be match between the cell and the instrument. And we base on the very customized approach to that. So yeah, that's maybe I will not go deep, but anyway, we provide those integrated spectral solutions together with the cell for a specific need. Then also with the cell should come with a broad range of electrodes, which we supply either made of metal or carbon allotropes. And also a limited range of chemicals. We only provide those that are useful in the electrochemistry lab. And also recently we started to provide membranes, which are pre-cut to the specific size that fits to our cells. And together with the VS particles, we are planning to coat those membranes with the catalysts. And I'm still speechless after the previous presentation, which was great. So we can actually provide those membranes, those membrane electrode assemblies to scientific community. And we have also many other projects running. Now we are focusing mainly on fuel cells, electrolyzers, and redox flow batteries. But also we are addressing some projects to industry. But yes, our main target is academia and research and development centers. But also we provide some kits for school laboratories and also solutions for industry, mainly silicon industry. We provide setups for electrochemical processing. And we are located in Norrköping in Sweden. And I'm talking to you right now from this corner office here. And here we have a research and development department, but also we have an assembly and distribution line in Poland in the center of energy in Krakow. So when we were starting the company in 2015, there was some pre-existing market. And we had some competitors, but actually we left them behind. And that's because when we started, there was no setups with the combined functionality, and there was completely no standardization in that field. And there was no samples no setups for samples with a non-standard form. And all these companies, they sell products off the shelf, so they don't allow any customization. And actually, we noticed that the tool market does not meet the needs of modern research. And also the number of players was very low. So that was a great opportunity for us. And then we try to be innovative at every possible level in this company. And I can tell you that this innovative thinking is probably one of the main natural resources in Sweden, together with the minerals, wood, and water. And even though none of us is Swedish, we perfectly fit into that environment, the business environment. Mm, and thanks to that, also the innovative thinking, but also a proximity to scientific community, we could develop products which perfectly fit the needs. And for that, we use crowdsourcing. So whenever we have a new series of products, we communicate that with the leading scientists in the field, and we harvest feedback so we can improve the product. And we, of course, award those participants. But the main thing is that the best thing of that is that the society gets better product. And we are quite young company, but we could, thanks to social media marketing, we became a leader of this sector in the market. And we have around 40,000 followers in social media. So whatever we post, we can it will be seen by most of the community, and we can reach every lab in the world in a few days. And also during this short history of the company, we developed a network, really broad network of distributors. We are covering, we have around 200 entities selling our products, and we cover every country with academia except North Korea and Vatican. But this is the most important part of my presentation. I would like to show you how we actually accelerate the development of catalysts. I just prepared this simple plot showing the whole advancement in that field. And that's actually all that is done. So what we are actually doing, those are not plans. We are doing this in the company. So it all starts with the bigger type cell, which is typically a first approach in the lab. This is a very low complexity cell, even though it looks a bit crowded. But there are a few problems related to that configuration. First of all, there is no inert atmosphere above the electrolyte, and we need some holders to arrange electrodes, and this arrangement is not reproducible. We need some clips or crocodile clip to immobilize the sample and also provide electrical contact. And this clip usually is corroding because electrolyte is filling up the contact with capillary forces. So in many cases, we may just measure the corrosion of the clip. And also this make a problem with the definition of the active surface area, because we are not dipping those electrodes completely. And the first solution, actually, in our history of the company, we did for that, we developed a series of cells to address that problem. So we developed those dedicated and optimized electrochemical cells, which are gas tight. They have a fixed electrode assembly. They have inert holders which do not contribute to the reaction. Also well-defined area. They are compatible with thin and thick films and also membranes, suitable for multi-response analysis, and they have many other advantages. So as I said, we have around 50 of those and still developing new. And new sections are appearing. So we could be completely fine with this. It could be a successful company selling those products out of the shelf. But that's not enough for our customers. So we have to go for a customized cells. And since the beginning, we treat customization as just another feature of the product. It's not an additional service. And of course, this is not easy, and it takes a lot of energy, time, and money. And also it brings a lot of risk, because if we increase complexity, then there is a higher chance for failure. But that's necessary, because the scientists bring up a novel concepts to the market, and they don't repeat experiments which are already published usually. And also they they want to match the measurement setup to the sample that they already have. So that's usually requires some customization. And there are many different forms of material in electrochemistry, and those are liquids, fine powders, macro particles and fibers, thin films, patterns, membranes, and even 3D objects. And we always have to, before the experiment, we have to combine them with some kind of current collector to form an electrode. And as you see here, there are many empty fields because there is a limited choice for that. And that's why, yes, that's the main reason to make customized cells. But then actually the core of our business is to integrate electrochemistry with other techniques. Because we want to harvest many different responses at the same time using one sample. And that's important because we can then easily draw conclusions from that experiment. And then there are many responses that can be collected. There's electrochemical, spectral, thermal, fluid dynamic, presence of gases, and even mass spectra. But still, there are some limitations in the design, and mainly because of the space limitations. Still, those sizes of probes and sensors are too big to be integrated in the small cell. And also there is a limited material selection for probes and sensors. So it's quite easy to make this in the aqueous solutions to integrate other techniques. But if we are thinking about the reactor for organic synthesis operating at high temperature, this is getting difficult. So, but the main thing about multi-response cells is that we are trying to increase the multi-hyphenation of those systems. So we want to combine electrochemistry with spectral techniques and just to exploit the advantages of both. And a good example of that system is Raman electrochemical quartz crystal microbalance flow cell. I have a picture of that. So here in this cell, it looks quite simple actually, but we have a sensor here, a QCM sensor, and the upper electrode of that sensor is coated with the material, studied material, or it's like it's our electrode on which we deposit the material. Then we have a set of electrodes, so we can control the potential and measure current, and at the same time, we are monitoring the spectra, Raman spectra of the cell. Of course, we record the resonance frequency of the sensor. So all this at the same time then can be combined in the analysis, and it should give consistent results. And there is another challenge in cells, which is merging features of the cell. But here we are talking about the cells that are already optimized. So it's not about making them more compact or smaller. It's about reducing the number of components in order to increase the performance and also limit the parasitic phenomena in the cell. And there are many different features of the cell that can be merged. So the most simple is like merging active electrode material with a current collector and electrical contact. But also other components of the cell can be merged. Still, there are some limitations in this process because we have a limited material selection, and the materials that we are using are mainly PEEK and Teflon, and the best machining way is just CNC machining, the fabrication technique. So there are limitations also in the fabrication, and still there are limitations in additive manufacturing. So this field is evolving very fast, but still it's not good. There are no solutions for us. But I can show you a few examples. So this is the bulk electrolysis cell with the merged features. In this case, the vessel, the beaker in which is holding the electrolyte, it's at the same time a working electrode. So that's we reduce the glass container, and we get the high surface area electrode, which is easy to clean. So very simple thing, but it gives a much higher value to that product. And that's another cell. It was designed for the electrochemical filtration. In this case, we have also the glassy carbon cathode, which is normally filled with some kind of adsorber. Most probably that would be a activated carbon. And then it's closed on both ends with a PIC mesh, and we have a boron doped diamond anode on both sides. So, the cathode, it's an electrode, it's a current collector, and at the same time, it's also the absorber bed. And then the last example in this section is it's a Photobio electrochemical reactor for microbes. And just by using stereographic printing, we could merge the aerator, which is important in this case, here at the bottom. And this part, the chamber of that cell, could be printed at once. And the material is also unique because that's a glass composite, which is seen by microbes as a glass. So it's approximately an inert material for them. But then another step in this advancement path is our automated systems. And it was already mentioned today. It's important to speed up the work in the lab, and also we noticed that the presence in the lab is not always possible. So this is an example of the robotic lab assistant from KUKA, which is operating with a chemical labware. And so as you see here, the example of the cell from us is it looks completely different because there are completely different requirements for people and robots. So this is the example also. So it has to be manipulated by the robotic arm, and also the electrical connections has to be done in a different way. But this may significantly accelerate the research. And then we have another step, which are microfluidic cells. There will be another talk after my talk on that topic, but we never actually talked about this so I don't know what to expect. But our main the main challenge in this project is to actually transfer all these cells that we have into the micro scale. So we want to integrate microfluidic channel with the microelectrodes and allow multiparametric in situ analysis. And then, so at the beginning of this project, we raised a hypothesis saying that scaling down of electrochemical cell to micro dimensions improve the cell performance. So we will have less problems with the parasitic effects, and we will extend its functionality. So the overall goal of this project is to develop first of its kind multiparametric instrumentation that will integrate electrochemistry inside the microfluidic chip together with other spectral techniques. So that will be a very powerful tool, and we want to allow deep customization of that platform. And yes, we just believe that this is the future of the laboratory analysis in electrochemistry. And the first step to that was development of those small cells for screen printed electrodes. So those electrodes are still not micro electrodes, but that was already it gave us an idea and the feeling how we should proceed. And so the work in this project was founded by Norwegian funds, and the project is called Upturn. And our consortium include the SINTEF that covers microfluidics, and some academic partners from Poland, Polish Academy of Science, and also Gdańsk University of Technology that develop the advanced materials for microelectrodes, mainly boron doped diamond. So this microfluidic chip integrates microfluidic system integrates a chip together with microelectrodes and a specific chip to platform interface, and everything is placed in the platform, which integrates the chip with other spectral techniques, and also sources of light, flow control units, pumps, and everything what's needed to run the experiment. So and the reason of doing that, it's actually now we can operate with the cells which are typically between 50 and 1000 milliliters. So even if we go for the flow cell, which is below 1 milliliter volume, we still have a tubing and reservoir. So this is not the best solution for experiments with the bioanalytes, pure ionic conductors, ionic liquids, and nanoprobes, mainly because of cost of these materials. And another reason is that when the classical electrodes are quite big, so the smallest plate electrode we provide is 7 by 7 millimeters. But even if we use disc electrode with a 2 millimeters in diameter, we still we are in the macro scale. So when we make those electrodes in the size of below 100 micrometers, preferably between 5 and 10, they will be advantageous because we will minimize the solution resistance effect. So we will be able to measure even diluted electrolytes, and we will have much higher response time, much faster. And then there are also many other advantages of having this configuration. And that's because we have to remember that every electrochemical cell is not an ideal current source. We have all these nonlinear behaviors, parasitic capacitances and resistances. The electrode is always aging, and the electrolyte is decompositing. And there are many other problems which probably we don't even realize. So when we scale down to microscale, we can get rid of most of them. This is just to show you the idea how we can convert this classical electrochemical cell, which has 3 electrodes, and into the channel. So we have one channel, and actually in this channel, here we have the structures of 2 cells. So I didn't put any conductive tracks here just to make this more clear, but I will show you magnification. So here we have a working electrode, which is like 100 micrometer in diameter. And then on the other plane, we have a counter electrode, which is twice in the size of the diameter. And very close to that, we have a potential probe, which is in this case, it's also the layer of gold. So using this simple structure of electrodes, we can actually get much better results when using the basic one. So then if we need a flow cell, the configuration is very similar, but instead of small electrodes, we just make them larger. So those are much longer electrodes in this case, only the potential probe stays the same size. And just making this functional design for every cell that we have on our page, we realize that we can actually make every cell in the micro scale. Even we can integrate spectral techniques easily. So in this case, we have a channel, microfluidic channel, which is the same width of 200 micron like before, but there is a larger opening here, and that's the chamber for the interaction with light. In this case, we have a working electrode on the bottom of the chamber on the silicon plate, and then we have a platinum electrode on glass plate with the opening or interaction with light. And in this case, the reference electrode comes from the bottom, and this is like also all microfluidic channel, which connects to the classical reference electrode. So it's like a login capillary for that. And then you may wonder what will be the last step in this path. Maybe some kind of nano electrodes, but not yet. The last one is related to multiplexed electrochemical cells, because we want to allow high throughput and also multi-parametric characterization. So not only that we harvest responses, but we also want to change factors in which are set for that experiment. And currently, it can be done by just multiplying the cells, classical cells, and using one of the multi-channel potentiostats. And that would be completely fine in many cases. But if we want to make the same analysis in the disposable device and apply statistical methods like design of experiment, this is not the best choice. Because we have to control also factors at each cell separately. But when we go for the chip, and if we just multiply this structure a few times, like in this case, we have 5 the same structures on one chip, then chip can be reusable, but it's in some cases it's a disposable chip. Then we can actually apply 5 separate experiments at one chip at the same time, harvest all responses, and using statistical software, we can build up the model and get immediate answer about the performance, and even we can find the optimum conditions for that experiment. So that would be actually all for now. I expect that in the near future we'll expand this plot because we get the contact from community and we are still challenged by them doing some new projects. But maybe I will talk about this next time. Thank you very much for your attention. If there are any questions, I will be happy to answer. Please just raise your hand and we will see it.
Thanks, Pawel, for this great overview. I just want to mention, you already showed it in your presentation that both the membranes that we developed with together with Fontini and Dipper we are trying to commercialize them through Electrochemical to make them available for the research community as a new benchmark in their research. And we're also trying to optimize our the new product that we are introducing beginning of next week, the PS particle nanoprinter, to make it optimal for the printing of the materials into those microfluidic chips. I'm not sure how much Mathieu will also cover this in his next talk, but now I would at least give him the floor for some questions. Mathieu, go ahead.
Yeah, so thanks for a very interesting talk. I was triggered by one of the designs I think you showed on slide 57 or 58 or something. And my question related to that is how you make sure that you get sufficient, let's say, uniform current distribution. Because if you make your volume small, of course, the resistivity goes up. I think it's 57 or something.
So that's microfluidic.
Yeah, the microfluidic design with the let's say the disk as counter, and then
yes,
this yeah, I think that was the one with the visual imaging capabilities from the top.
Yes, so this one.
Yeah,
so those are still functional designs. So we don't have a physical chip in hand, so we can't test it. Yeah. That's in the next iteration, in the next production batch, we'll probably have to align those designs. But in order to harvest the first input, we need to agree about some design. So I cannot address that question at the moment.
Okay. Yeah. Thanks.
Thanks for the question. I just want to also coming back to what Charlotte mentioned is that standardization is very important, and I think getting a common idea about the best design of these microfluidic chips is very important because it also enables us to discuss the standardization. So how should we standardize an experiment, and how can that be automated in a certain sense or accelerated? So I think this is very important. Any other questions? I'm not sure if you mentioned it, Pawel, but when do you expect these microfluidic chips to become available on your web shop?
So SINTEF, I know that SINTEF is already finishing design of the masks for processing, and at the beginning of the next year we will have already first production batch with us, and that will be tested by our academic partners.
Great. But then in the somewhere Q2 or Q3,
Yes. So yeah, the end of the project is actually so we still have 2 years to go. So we had just accomplished the first year of the project. But then, so the chip is, of course, it's a challenge to make it and combine with electrodes and find the proper configuration of those electrodes and also dimensions between them. But then another challenge is to design a platform that will combine this chip with other techniques. So that's something we already work for some time, and this will evolve also with the chip. So I think that the first commercial product will be released at the end of next year.
At the end of next year. Great.
Yes.
Any last questions before we are moving over to our next speaker of today, Maciej Rodaj, which already was visible on his question? If not, Pawel, thank you for this elaborate overview of the evolution of these